All right. Greetings, everyone. This is Mrs. Wigton and Maisie. And check out those ears. Aren't they fabulous? It's Maisie, the Mexican hairless dog. And she is not a bat. Not a bat. She wears clothes. All right. And I just want to remind you, since it's been a while, that I always feature Maisie at some point in my show, in my episodes, but that I am a lead learner who is not a scientist. And I'll say hi here. Hello. And this is I've started these videos. I'm going to start moving over here to come see my corner where I work. In order to help my son get through challenge 1, who had profound dyslexia. And so this is why I've been doing these, except that we got burnt out at the end of the year and we just dropped off. And so here we are a year later. I'm making a valiant attempt to finish the project I started. So for those that were following last year, I'm so sorry. We just did our best. And this year I am sick. It is spring break and I am determined, whether I'm sick or not, to bust through those last few chapters and get it out to you guys. So this is module 13, the beginning of it, from the Exploring Creation with Physical Science 3rd edition student notebook. And we can dive right in, okay? Let's see here. So we have, first and foremost, atmosphere. We're on page 390. Atmosphere is the mass of air surrounding a planet. Ooh, I feel like we should have some really cool music there. All right, this next one has lots of holes, and all of the answers are right here on page, where are we at? 468. And the actual text. And in it we have, so should we write them in together? We have oxygen, which is O2. We have nitrogen, which I think is just N. And then we have all other gases, including, oh, it's N2, sorry, N2. So including the nitrogen, the oxygen, we have argon, we have carbon dioxide, which is CO2, which you want to memorize that one, neon, Ne, helium, He, ooh, there's so many others. There's like more than they have room for. And we'll just do the next one, which is methane, which is CH4. Okay? But they have like krypton and hydrogen. They are the least, though. Okay? All right. What are the two gases in our atmosphere that are essential for life, and explain how they are used? First, we have carbon dioxide. I told you that's a super important abbreviation you want to learn because we use it all the time. Carbon dioxide is when photosynthesis turns carbon dioxide into food. This is why it happens. And plants need that carbon dioxide to live and to put out oxygen for us to breathe. And so it's this really cool symbiotic relationship we've got going on. And oops, I wrote water, H2O, but no, it's oxygen, O2, just plain old O for oxygen with, that has the two ions there. Let's see, are produced as a byproduct of photosynthesis. We need oxygen to live and put out CO2. Okay? So remember, if I'm going too fast, one idea is to just listen first time through, second time through to try to like write in stuff, pause it as you go. But what I'd have my son do is listen to my videos every day, once a day, during the week that he was supposed to read that. And so that it kind of really got stuck in his brain. So list the other things mentioned in the text on page 469 that our atmosphere provides for us. So what does our atmosphere do? It provides the water cycle, cannot be completed without it. The weathering of rocks, weather in general, like all weather, protection from meteoroids, protection from too much sun. It provides the medium for sound waves to travel through. Now that really blew my mind. I'm telling you what. It provides the medium for sound waves to travel through. What does the atmosphere? Because the atmosphere has mass. What is it full like? What is the mass? Well, all of these things make it up. The oxygen, the nitrogen, and all these other little things, including sometimes water. And so, sorry, there's all the noise in my house right now. I've got kids in the shower. I have squeaking kids in the bedroom. They're just making crazy noises with each other. Sorry about that. But they're having fun. I'm happy. But I just never thought about that without that, like you think about up in space, there's no mass to the air. It's just space, right? And so I don't know that there's anything for the sound waves to travel through. So you probably wouldn't hear a bird tweeting on the moon if it could live on the moon. I'm just picturing a bird in a little spacesuit now. Okay, we're going to move on before I go down some crazy lane there any further than I have. Greenhouse effect. All right. This is the process by which certain gases, mostly water vapor, carbon dioxide, and methane, how they trap heat that radiates from Earth. So I'm going to say that again because it's kind of big words and crazy. Greenhouse effect is a process by which certain gases trap heat that radiates from Earth. Okay, and so gases are getting trapped. Gases trap heat. That's what it is. Not gases the heat is getting trapped. So imagine here's the Earth, and here's the gases in the Earth, and then the heat will make the heat go the other way, gets trapped in that. That is the weirdest nondescript picture, but the gases are trapping heat is what it's saying is the greenhouse effect. Okay. The greenhouse, what does the text say is the difference between the terms greenhouse effect and global warming. Okay. Greenhouse effect helps maintain our perfect living conditions on Earth for humans and plants and animals. Global warming is too much of a good thing, and it warms up the Earth too much. Okay, so, oh my goodness. Sorry, I can totally hear every word my kids are saying. Where does the carbon dioxide come from? Fire and breathing are both combustion reactions that create carbon dioxide. So, as I talk to you right now, I am creating carbon dioxide. All right, on your own. They're asking here, this long thing. Why do some houseplants tend to grow better when their caretakers talk to them? Well, why do you think? Because the carbon dioxide that we breathe out is exactly what they need to live. And so I've got this beautiful plant here that is not doing so great because I have not been talking to it enough. That's the story on that. It's nothing to do with the fact that I'm a horrible indoor plant caretaker. I just need to talk to it more. All right, let's turn to 392. Pressure is defined by the force or weight applied over an area. Atmospheric pressure is the amount of pressure of the atmosphere on everything. I find this really fascinating. So there's pressure because there's mass in that air, and then there's gravity pushing down. So here it is, gravity pushing down on the mass of the air in our atmosphere. There's an actual, like they can actually weigh it and measure it and say, here's how much it is. There is at sea level 14.7 pounds is pushed down on every square inch that it touches because of the Earth's atmospheric pressure. It's not just, it's because of the gravity pushing down on it, okay? So isn't that fascinating? I find it fascinating. All right, hopefully you do this experiment in your class, and you'll see what happens to the lack of pressure coming on the inside, and you'll see what happens. It changes the can completely because of pressure. All right, list all the units that are used for atmospheric pressure. Which ones do you need to know for this course? All right, so barometers use a measurement called barometers, is what they said. Millimeters of mercury is mmHg. And my husband added that millibars of mercury, or inches of mercury. So millibars is what they use. He's in aviation, and so I'm thinking this is what he said was the European two measurements, millibars or millimeters, and then we in America more often use inches of mercury. All right, we've got the atmosphere, believe it or not, is an actual measurement, ATM, hectopascals, sorry, hectopascals, HPA, and the torr is another measurement of for atmospheric pressure. Which ones do you need to know for this course? Just the atmosphere. Here you go, right there, and I think it also listed some sort of measurement that was not listed there. Let's see if I can find it. Wow. Okay. And it says in pounds per square inch. So that's the other one. Okay. All right. See figure 13.7. Let's look at that. Altitude and air pressure. I love this. All right. The gas molecules that make up air are most dense at ground level. See how they're really, really dense down here, meaning more concentrated. There's more of them, all the molecules, and then they get fewer and fewer as we go up, higher and higher and higher. This is, whoop, there's the airplanes. Wow. There's Mr. Wigton flying the airplane. Just kidding. He's a fixer of the airplanes mostly, but he can fly them too. Let's see here. So they get less and less the higher you go up. Therefore, there's less oxygen up higher and less gravity pushing down on you because there's less for it to push down on in the air, right? There's no, see, all the molecules aren't there for it to push down on. So that must make it easier to fly up there too, right? Pretty fascinating. Oh, I'm turning the wrong page here. All right, on your own. Let's see what we got here. How does the atmosphere protect life on Earth? Well, it provides oxygen and carbon dioxide essential for life, for humans and plants and animals. Secondly, we need the atmosphere to complete the water cycle. Just a review, water cycle is evaporation, when the water comes up off the earth. Condensation, it condenses into clouds. Precipitation, it comes down out of the clouds. It starts over again. It's like a circle of water. It shields us also from meteoroids and other space debris and harmful UV rays and high energy radiation. And also helps us maintain a temperature here on Earth that promotes life, meaning without this perfect, there's two things here that if they weren't perfectly like they are in our atmosphere, we would die. We would not be able to sustain life on Earth. And that is our oxygen level. Of course, we need water to live, actually, so three things. And the amount of sun that we get. If the temperature was too hot, we'd all burn up. Too cold, we'd freeze to death. And it's just perfect because God just made it all work together in that way. He totally designed this earth to sustain life. So it's so cool. And this is super cool. It allows us to hear things. Like I mentioned, sound waves need a medium to travel through. All right, 13.3, air pressure decreases as altitude increases. I always like to draw these little graphs that totally extra for you. This is called inversely proportionate. When a graph is inversely proportionate, it looks like this. And as one is going up, the other one is going down. Okay? There's air pressure and altitude. That's what happens. And that's what we were seeing here. As one goes up, one goes up, the other one goes down. The number of dots and the molecules and those things, right? Okay, that's what that's demonstrating. 13.4, you can see me, it's not the answer. I didn't circle the answer on purpose. The atmospheric pressure is 1.1 atm, remember atmospheres. Which of the following values for atmospheric pressure would you see in the weather report? Well, at 1.0 atm, it equals 29.9 inches of pressure. So it has to be, because it's 1.1, it has to be more than that. So which one of these is more than that? I think we know. There's only one choice, right? So let's circle it. That's it. By George. That's it. Ready? Moving on. Right. Radiation. The transfer of energy by waves through air or empty space. That's what radiation is. Transferring energy by waves through air. Conduction. Transfer of heat energy from molecule to molecule by contact. Convection. The transfer of heat energy through a liquid or gas by currents. So they had you use a graphic organizer. You can write words in here to explain them yourself, or you can draw pictures like I did. Radiation is when the sun finishes warming up the earth. It starts to radiate heat back up off of the earth onto us and all the other things on our planet, and saying, oh boy, we've got excess heat here. We're good. Conduction is when I stick a metal spoon in my tea, because I'm not a coffee girl, so, and and it gets hot, and it has conducted that heat from the hot tea through all of the molecules connected in the spoon. And if it had been a plastic spoon, well, by George, that's an insulator, not a conductor, right? So that would not have, I would have not burned my hand. And so conductors are metal usually. All right, convection is when cool air is denser than warm air. Let's see, I wrote a thing that says, see, there figures this, I did a crude interpretation of figure 13.10, and here's a much better version of it. Ready? Convection cloud formation. So you can see what's happening here is the cool air is denser than the warm air, so it falls down, and then it warms up the warm earth, and then the heat rises and goes back up into the air, creating clouds. See here, and here's what we can explain more about that. As warm, how does the cloud form? I'm coming back over. Try not to get sick here. As warm, moist air rises, it cools, and then the water vapor in the cooling air condenses to form clouds. Isn't that cool? All right. Condensation, people. All right. We're cruising. We only have 2 more pages left. Heat for this half is energy that is transferred as a consequence of temperature differences. I love this section. I'm going to tell you, I learned so much from this chapter already. I'm only halfway through it, and I'm like, whoa, blowing my mind. A measure of the energy of random motion is in a substance's molecules is temperature. So it's measuring the energy of random motion. What? You thought it was going to be about heat or something like that, but no, it's about energy. So that's what blows my mind. Here it goes. What's this? Really good picture. A substance at high temperature. Do you see the longer arrows? That means they're moving faster. And the low temperature ones, they're just like we're just moving a little bit. The heat flows from air, always flows from an area of higher temperature to lower temperature, and you see how it's starting to infiltrate the lower temperature stuff. It's like, hey, we're going to transfer some of our excess energy to you. It says, use a figure to explain. Well, it measures kinetic energy of molecules in a substance. That's that movement. All right, on your own. This goes a little, I think this is really important because it explains a little bit more. This is saying we've got 2 bricks, right? The first brick is -1 degree Celsius. The second brick is -10 degrees Celsius. And these are both very cold bricks, okay? So it's like, well, the question is there any heat in this 2-block system that are touching? And if so, how will that heat energy be transferred? Well, as I said before, the second law of thermodynamics states heat always flows from an area of area of higher temperature to an area of lower temperature. And so the transfer of heat energy happens because there's a higher temperature, a lower temperature. It's going to flow down into that colder from the warmer, even though it's not hot. And that transfer of energy means, quote, heat is present. Even if it's not hot, heat is just that transfer of energy. Okay? So that's a yes, it did. All right. The thermometer reads 25 degrees Celsius. Suppose you put that into a liquid, and the thermometer reading increases to 80.17 degrees Celsius. And somebody says, wait a second, that was actually higher than that. The second you put that thermometer was put in it. Are they correct? Why or why not? They're saying this is super hot. And this is 25 degrees. They put it in the water, and it's suddenly 80 something degrees. And they say, wait, that water was actually a little bit higher than 80. This is what they're saying has happened. And according to the answers, yes, the astute observer is correct, because that water transferred some of its temperature, some of its heat energy to the thermometer when it was put in. And so it was higher, and then it got put in, and the temperature of the water lowered. And this doesn't even cover in this book something so cool that I just want to just add really quick here. One of my favorite things I learned from this section is that this is why we are hot or cold, is because the molecules in our body are moving super duper fast when we're hot, and not as fast when we're cold. And so I just think that's wicked cool that that's what's making us hot or cold. It's not the outside as much as that transfer of energy into us and what it's doing to our bodies. So thought that was super cool. I hope you have a wonderful rest of your day, and take care. Bye-bye.